Question 16. A thunderstorm cloud is located above flat ground. The lower surface of the cloud is at a height of 400 meters above the ground. The potential difference between the cloud base and the ground is 120 megavolts, producing a uniform vertical electric field in the region. A small water droplet carries a charge of 3.0 times 10 to the minus 12 coulombs and is suspended midway between the cloud and the ground. Which value is closest to the magnitude of the electric force acting on the droplet due to the electric field? This question tests our understanding of electric fields and the relationship between electric field strength and electric force. What do we know? In a uniform electric field, the force acting on a charge is the same everywhere within the field. The electric field strength between two regions with a potential difference V, separated by a distance d, is given by the relation E equals V divided by d. And the electric force acting on a particle with charge Q in an electric field E is given by the equation F equals QE. Let's think through the solution step by step. We begin by calculating the electric field strength produced between the cloud and the ground. The electric field strength in a uniform field is given by E equals V divided by d. The potential difference given in the problem is 120 megavolts. To work in standard units, we convert this to volts. 120 megavolts is 120 times 10 to the power 6 volts, since mega corresponds to 10 raised to the power 6. The distance between the cloud base and the ground is 400 meters. Substituting these values into the equation for electric field strength gives E equals 120 times 10 to the power 6 divided by 400. Carrying out the calculation gives an electric field strength of 3.0 times 10 to the power 5 volts per meter. Next, we calculate the electric force acting on the droplet. The charge on the droplet is 3.0 times 10 to the power minus 12 coulombs. The electric force on a charge in an electric field is given by F equals QE. Substituting the values gives F equals 3.0 times 10 to the power minus 12 multiplied by 3.0 times 10 to the power 5. Multiplying these values gives 9.0 times 10 to the power minus 7 newtons. So the magnitude of the electric force acting on the droplet is approximately 9.0 times 10 to the power minus 7 newtons. This is our final answer. What did we do? First, we calculated the electric field strength between the cloud and the ground using the relation E equals V divided by d. Then we substituted the charge of the droplet into the equation F equals QE to determine the electric force acting on it. Because the electric field is uniform, the value of the force is the same regardless of the droplet's position between the cloud and the ground. Potential misconceptions to watch for. Students often substitute the potential difference directly without first converting megavolts into volts. This leads to an incorrect value for the electric field strength. Every quantity should be in SI units before substitution. Another common mistake comes from the statement that the droplet is midway between the cloud and the ground. Some students assume that the electric field is weaker there, and therefore use half the separation distance. However, in a uniform electric field, the field strength is the same at every point, so the electric force on the charge remains the same everywhere in the field. Key points to remember. The electric field strength in a uniform field is given by E equals V divided by d. In a uniform electric field, the field strength has the same value at every point between the two regions. The electric force on a charge in an electric field is given by F equals QE. And the position of the charge within a uniform field does not change the magnitude of the electric force acting on it.